Continue. Our third talk this morning is by Professor Shou-Wu, who will talk to us about heights of algebraic cycles and special values of L series. Welcome.
Thank you, and I'm sorry to change the title. Originally, I want to give a talk in differential geometry because it's called a plenary talk. Then later on, I found a schedule, the plenary talk in number theory and algebraic geometry. There also the parallel section in algebraic geometry. So I don't want to compete with other groups. So yeah, I go back to talk about number theory. So I think one of the greatest mystery in number theory is that why the zeta function or error function plays such a big role in arithmetic problem. So if later on my talk be very technical, but go back to history from 77, Euler proved that the product formula. So basically that the product even the one p minus 1. Then we know that when s equals 1, this side is infinity. So this implies that there's infinitely many. Of course, this theorem already known Platon, but this proof is such more precise, and later on become a very important the tool in the number theory. This is basically the first time. The 100 years later, then the Dirichlet introduced the Dirichlet error function. It's again so chi is a character z mod nz, z cross, and so this gives they have a name for that. Then he, in fact, it's a precise formula. It's a precise formula. It has a formula for that. For people who are interested in this topic, you best can deduce the formula by yourself using a simple Fourier transform over finite group. From this one, it shows that there's arithmetic configuration. Right. So basically show that so for any A, M, then the primes is congruent to A. Oh, let's put X over. Well, this is infinite. At least you prove this. Yeah. So not only that, so this formula also give later on. This formula gives not only for non-vanishing, the formula also give you the class group and the units. Is provided as the most important one of the most important tool to study the modern number theory. Then 100 years later, Artin introduced the error function representation. GLNC. The similar class A introduce error function. Zeta function for content modular units, the rational points. For varieties over finite fields. Then I make a product of this thing. And then, of course, and this kind of error function can be used to prove the generalization of these arithmetic progressions. For example, the Chebotarev density theorem. This one has become a very important tool to study rational points at the DSP campus. This time it's rational. So it's a quite amazing story that error function in number theory already they are with us for a lot of 300 years. So in the new century, so today's talk, I will more formulate to the 21st century. So there's a attempts, at least in the last 20 years, the attempts to study not only for rational points, so then error functions, or special value error functions to study algebraic cycle. So we have some partial, it's very difficult as usual, but still we have some partial results. And again, in this lecture, we're not going to define anything. But I will give you some flavor how the analytical objects be used to study arithmetic. So maybe I will talk about two things. I will review the Kurosawa formula. That's one of the most important theorem proved about 50 years ago and 40 years. And then I will go to, in the last 20 years, we're trying to generalize the theorem to the triple product of error function. Any question? Okay. So now I go to the detail. I'm sorry, still, Who is the elliptic curve? Over rationals. And so E of Q is this is a group. So this is known to Wang He in the beginning of the at least formally written lecture probably much earlier. You have a P and a Q of R here like an S. So about the model 100 years ago, the model proved that E of Q is finite generated. So basically means that if there's a finite many points, and the elliptic curve which can be used to generate other point. By the two rule, you can either make a line pass the two points, get a certain points, or you can make a reflection rather. So this is of another rule. So this is the final rule. Can you see this thing from back? And for this group, this thing is not very big. So this actually cardinality is less equal than 16. I believe this is a measure 977. It's not easy, at least this one, no? So the difficult problem is trying to understand. Problem trying to understand what is allowed. So in the 1960s, the formula that the PSV conjecture related to this R to be called the order vanishing of S. And of course, when the formula conjecture still don't know this thing has a holomorphic continuation or not. And then now, of course, it's the theorem of Amorous. This actually has a holomorphic continuation. So let's say, so this LE of S is the product P divided N of 1 minus AP P minus S, and the P not divided N 1 minus P S plus P 1 minus QS. N is a conductor. So this AP is plus minus 1 or 0. So this AP, it can be obtained by AP. P minus AP is number of solutions. So it's the 1970s. So when it has CM, then we know that if L E and 1 is not 0, because E over Q is finite. So this is the basic profile. Then there is a Gross-Zagier formula. So that if the conjecture is true, basically this is a weak form. Weak form true. Plus if the order vanishes, let's go that. This is a Gross-Zagier plus polynomial. And of course, recently there's something called the converse theorem, trying to show that you can start with an algebraic rank, get a similar result. Okay, so I want to explain So how the Gonzaga proved the theorem? This is very hard. Why? Japanese you read but you don't have Japanese machine to cut out. That's the machine, you know that. So the idea is the following. So the idea is to start E, S, to write an N to the S. Then they form the modular form. And then from these, you can make an integration to C. Just make integration. Tau goes to pi infinity to tau of L this form. And Q equals pi I tau e tau. Then of course this is the form, but this is the modular form. Yeah, I mean when Gonzaga from the theorem they assume this E is modular. I mean this is a modular form. Of course later on it's proved. 10 years later by analysis is actually every elliptic curve of Q is modular. First four semi-stable are completed by others for all elliptic curves. But anyway, you can formulate this in. This will give you, but since this guy is invariant, so FZ is invariant, gamma naught of n. So you can formulate these the quotients. You see on the lattice, the lattice impurities. This is actually isogenity ordinary. So anyway, from the whole thing together, you get a map about the pi. One beautiful thing about this guy, we give a name called X naught of n. The X naught of n itself, the modulus space. Of isogenous. Sorry, too many elliptic curves here, but these two just elliptic curves of a complex numbers. And the kernel of phi equal is isomorphic Z mod and Z. And yeah, but if both U1, U2 have same composition, then the phi define the points. Okay, the phi is define the point. Is a point of X naught of n over some it's positive. It's abelian extension of by k, for example. Okay. So that's a very, and this modular curve, they have a dense set of algebraic points, very explicit. That's a very important thing. So you if you take the pi of points, that this will become elliptic curve of algebraic points. So you construct algebraic points from some points on the modular curve by very explicit construction. So then if you take the Galois, if you take a trace, sigma inside the Galois group of h of k, so the radical yk here, this will be elliptic curve E of k. So you get such a points, right? So you construct the points here. So this is a really amazing thing that is started. If the elliptic curve can be parameterized by a modular curve, then you get a supplemental of elliptic curve. But of course, you say, okay, elliptic curve can be parameterized by complex plane. But from a complex plane by Weierstrass function, you can say in a complex plane, I have a lot of points. But we have no idea to see which points has image, which is the algebra, right? Because complex, the beautiful thing, this is a modular. This map is algebraic. So there's a very miracle way to think of the modularity. The growth and the Zagier, what does that prove? Is the following. So if you k, let's specify not by k, by O, the ring of integers. Okay. The growth Zagier show that the arrow EKS at 1 will be 0. At prime EK1 will be some norm of YK and YK, some constant. So LEK S, the product two error function, LE choose by D of S. So in other words, E is defined by y squared equals x2 plus x plus b e to the d, maybe like next. Okay. It's a minus d y squared x2 plus x. So this is one of a very surprise result that the error function can be used to construct rational on elliptic curve. And the theory is not complicated. Of course, the proof of such a theorem is it's a little bit, I mean, so it depends which level. I think the proof, the original proof is really checked by piece by piece. Now I give you a few remarks. Yeah, Kolyvagin thing just say if the yk is non-vanishing, then your elliptic curve is generated by this point. And then recent one, I think the Chris Skinner, Wei Zhang, and Ye Tian, they proved the converse theorem. The first two trying to prove the converse theorem for non-CM elliptic curve. Ye Tian trying to prove for the CM. But basically, we have something converse theorem is true. If the model A group is at the rank at the most one, then the error function has vanished out of the atmosphere. So I get that's it. Yeah. So there are two remarks, and another remark is that the Common theorem the theorem is by inner region and Etienne. Probably have some collaborate there. The second thing is the theorem is the proof for any modular abelian varieties over total real field. Now this is it's done by my collaboration work with Yuan, Wei Zhang, and myself. So it's very interesting that with the modular there. So if you listen to Andy's lecture, you see the modularity is a very important assumption here. So we prove the theorem, but this is by no way, it's not the easiest thing because Taylor and other people show the potential modularity for such a geometry type. But so now the most urgent thing right now is trying to show that they are really. In this case, we can apply the theorem for much general situations. Okay, so this is a story in last century. This is like 40 years ago. This is complete about 10 years ago. And from beginning, after done with the growth idea, the next thing I want to do is about the triple products. Now it's a new thing on the triple product. All the same. Triple product for abelian varieties and the triple product for error function. So instead of we can start 3 unit curves. 3 unit curves. Over Q. So the what we care is about the curves in the ciphers. So we started the cipher. So this is a space group abelian groups of curves modular the rational equivalence. So give you some idea like that. Rational equivalence is done. You can never study on geometry. This is something like that. We have this the product of 3 unit curves there. So you have the U1, U2, U3. So suppose you have a cycle. So you have a cycle Z. There's summation like a 1C1 minus C2. So this is both an effective one. Effective curves. Cycle of curves. So you have a C1, C2. The C1 say equivalent C2 means that you can complete this in here, at least this in by a surface. So this is S in the surface. Of the surface, you can continue to move C1 to C2. It's not continue to rationally move. So this surface have a map to P1. So the P1, the C1 will be above F here. C1 will be by inverse of 0, C2 by inverse of infinity. In this case, we call C1 and C2 are equivalent. You can move a cycle from one to other. This is why I call it rational. Rational because this guy is rational. Curve. Right. This space is the people really want to study this stuff. For example, Taylor's conjecture, Hodge conjecture, that's for homology class. But what we care is about the homology trivial classes. The homology. Homology trivial classes mean that this S not necessarily, this S is algebraic. Homology trivial means that you can replace S by a complex manifold, right? You don't care it's algebraic or not. You just want to C1 to C2 a boundary of the surface. Homology trivial, homology equivalence. So this P1 is equivalence is simpler. They take S to be the smooth manifold. The boundary of S is C1 minus C2. So that's the about it. So there's two different ones. The rational equivalent definitely homology equivalent, but the converse is not true. Inside the space, there's the old space here. So let me write down CH of E1, E2, E3. There is a equal to of this n of the old one, direct sum of the new one. All of my mean that is the space comes from the product of C1. Say, for example, you have a C1, you have a C cross 0. C is a curve, the cycle inside. It's a cycle of E1 cross E2, for example. Or you can have E1 cross 0, cross 0. So this is the older one, right? This cycle from the older one. Then complements of this thing is the new one, right? So how do I get a new one? For example, the projected new one actually pretty easy. You do the following simple trick. So you just like this picture. So if you have some curve C here, then you can, this curve has many embedded. C1, this plan, C2, 3, or maybe, yeah, you have 3 plane you can have. So C has so C inside, C have some kind of a partial Cij. You take the partial diagonal, partial projection there, then you plot sigma Ci means that you project to the axis. In this way, it automatically gives you homological trivial cycle. Trivial and new. So let's write this in from C new. So one very special case of the conjecture formulated by Bellins and Bloch independently the following theorem. Only conjecture is that the rank of CH2 of U1 plus E2 plus E3 new one equals order of variation of error function of U1, E2, E3 of S. So this is a triple product. Of REI and S. So probably it's better to describe these things in terms of representation. So if REI S is L, say rho I, the theta module, for example, the theta module CLEI of S, right? So this is the 2x2 matrix with the action by Salvatore. And then it is a triple product. U2, U3, S, the L, CL U1, tensor tier U2, tensor tier U3 of S. And this guy, so if, I mean, at least when I form this question, the modularity conjecture is not proved. So if U1, E2, E3 modular, of course, then we know that's it's true. Then by Garrett, and completed by Telsby, Shapiro, and Rallis, that this error function has the analytic continuation to C with function equation Ls of epsilon S and the form minus the from is the epsilon S. So this is actually the product epsilon P of S. Here that's infinity. From this guy, you will get a quaternion. I will not try to describe. So epsilon 2 equal to plus minus 1. From this end. Okay, so that's the basic of the conjecture. And the conjecture is a bit really a conjecture. Actually, we don't even know that this guy is finite dimensional. We don't even know that the rank actually finite. No general theorem. We don't know which one is non-trivial inside. Just space. So this is a balance and something like that. 1980s is a bit of stranger. Yeah, the lot of conjecture was formulated at that time. So now we apply the modularity to this question. So anyway, from this from the local data, F&P equals plus minus 1. So let's assume the global is minus 1. Then you will get a subsequent Schumann curve. X. Similar curve is very similar to modular curve. Only difference that this guy is defined by quaternions. We're not going to explain the quaternions. Because the similar curve, then again by work of wires, I, and then you get this pi I here. This by Jacquet Langlands. So you will get the parameterization there. And if you take all these three together, you take a product, all these together, you will get pi 1, pi 2, pi 3. You get E1 plus E2 plus E3. So this abelian threefold has a map and a curve map inside the Schumann curve. Right? So definitely you have a pi of X. Then you take a new path. This will be the child group we care about it. New path. And so the one today is that so this L prime of U1, U2, U3 at 2 equals certain types of these cycles Ix new, Ix new. B here. Don't worry, just some quadratic. I is defined. And the remark is that, so if the conductor of E1 equals the conductor of E2 equals the conductor of E3, of course, this is basically conjectured by Gross and Kudler. And then the B is the theorem holds for any the product of any of three of any three modular in varieties. What? You can make it equal, but they vanish. If U1, E2, E3 equal, they vanish because it's given by basically the wedge product. There's something inside there because it's composed. When U1 equal E2 equals E3 is vanished, but E1 equal E2, but not as E3 is a very interesting case. And in that case, you get a new construction of the rational points. Yeah, you get a. Let me finish this and I come back to your question. Three modular in variety of probability of R of R. Again, modularity is a very important assumption here. It's really connected to the end of the lecture. Now I go to the here's a question. Question is like that: if E1 for E2 for E3, this theorem is 0 to 0, not interesting. So if E1 equal to E2, not isogeny. E3, this is actually quite interesting thing. This will be they have the following very interesting phenomenon. They have x mapped to u1 equal u2, and the map to u3. Okay, so what do? You pick up any points here. Yeah. Then you pull back to the points of P. You get a cycle here. Then you push it forward by 3. By 1 of P, you get a points inside this of Q. And this theorem simply said that the heights of these points, so the theorem simply said that the error of symmetric square of U1 at 1 times L prime U3 of 1, the heights of these points. Something like that. So there's a definitely good construction of rational points. But of course, still derivative, nothing, you can imagine, not really that much new. Any question? Yeah, so now I talked a little bit about the ingredient of proof. So the theorem is a most special case. The most special case, also called the GPP conjecture, an arithmetic analog. It's basically the first example of the growth idea. So this is the simplest case of arithmetic GPP. So in fact, you can think of this as O3 plus O4 and O3 inside here. You can think about the Shimura right defined the O3, O4. But this guy is split O3, O3. Right? So this isomorph, I mean isolated to O3. O3. So typically, when I do like a Grozangian formula or all these superproduct formula, usually when you do the same, there's a local theory and a global theory. There's a local theory. Are we not going to explain? There's a local theory. The local theory for both arithmetic and non-arithmetic sum. I think a local theory, there's a kind of a branch of the epsilon facts related to the linear forms. So this is basically the work by Rasak. Yeah, maybe in your PhD thesis, something like that. Right? And I will not explain. So that's very important. The reason is, if you have such a local theory, then you have a tremendous flexibility to prove the theorem. So you don't really need to prove the theorem by one vector. You can choose any vector you like. Unless, so this provide the flexibility. So in other words, it is not about the equality. So the equality of numbers becomes equality of two linear functionals. So somehow you have three automorphic representations. So this is the first representations. Then you have a pi 1, pi 2, pi 3. So this C and respect to the diagonal. So this representation of GR2. All these are all quaternions of E cross. This is something. So this is one dimensional. So there's a lot to tell you these things. Exactly one dimension. That's very important. Once you know one dimensional, then both sides. So the basically is about the left hand side. So you have a linear function of left hand side. It's a linear function of right hand side. So this we know both of them inside here, and we also know this guy is not vanishing, for example. So the question is, so this must be some constant C kind of stuff because this is one dimensional stuff. So basically, want to show. So you have two linear functions inside. One of them not vanishing. So they differ by constant C. The whole question is, okay, the error here. So the question will become, calculate this error. When you calculate the error, you don't need you can pick up any vector inside to calculate the error. You don't need to be very careful the new form or not. In fact, for this theory, new form itself is not that much useful. New form, there's one input, first input. Another local input is even Liu's work. So he showed that then he gave us produce plenty of test vectors for such a calculation. And because we're doing the global proof, we have to throw a lot of things out. So there is two local input. So now I talk about global input. We're not going to talk about local input. Local input are all representation theory, but you already listened to representation lectures. This is for number theory. So I take the global. The global theory is, as I said, that I have the error function here. S there. And I want to choose here. I want to prove this thing is some cycles. Z, I will multiply Hungarian. And this thing itself, my work of Garrett and Peter Rallis, this be integration of 3 GR2 cross GR2 cross GR2, but the fiber product GR2, GM, and certain 3 module forms, phi 1, phi 2, F1, F2, F3. The 3 module forms are associated elliptic curves with some associations. E of Z1, Z2, Z3 of S, Z1, D mu, Z1. Okay, let me say D mu, Z1, Z2, Z3. So what you do is that you have a. So the idea is that this have GSP 6. You have this group G here. You put the G inside. So this is a 6-dimensional space. Each of these guys has a 2-dimensional. So this is V we call V1, the rest of V2, V3. So each of them is a symplectic space, two-dimensional. You may direct some inside. Then you can embed in this group inside there. And here you can have, as I said, it is Z1, Z2, Z3. I mean, okay. So here, axon, this axon zero out of 3 space. So this is the matrix. C, which is symmetric, the imaginary of omega is bigger than 0, right? So then here is axon on H, H, H. But this embedded this stuff just by diagonal. You have tau 1, 0, 0, tau 2, 0, 0, 0, tau 3. Just embedding the 3 upper plane to the 0 upper plane. Then here you have as a series is restricted to this product, then this give you this size. For other sides, we have is the pi of x there, right? It's inside E1, E2, E3. Sorry. For 1 minute. So we have this x similar curve. We get inside x cross x. So this is a Shimura curve, diagonally embedded into here. And each of space you have high operators, T1, T2, T3. Right. So then you make the tech operators you can work on this diagonal. Okay, this is the new. Then you make this in the new cycle, then you formulate the band block Hyperion. Then you take a sum here. And 1 and 2 and 3, you get the form of power series, equal to 2 pi I and 1 tau 1 and 2 tau 2 and 3 tau 3. So this become a plus form or weight 2 on H3 with this group. So the idea will be to show this as a set series. So this as a set series, Z1, Z2, Z3, and the direct by the 2. Okay, originally it's as a set series, but if we restricted the diagonal, it's not as a set series. So you still can talk about the holomorphic projection. And then the idea is to show these two actually equal, right? But then in general, it's very hard to show they're equal. And then you have to do a lot of things. You first show they're equal, almost equal. The good coefficient are equal. That took like a few years. Then we show the bad coefficient equal. That takes like 15 years. So the 99% we know is true is 5 years. Like a 0, 0, very small, but yeah, in 15 years, just a long time. Just show that the singular coefficient are equal. This just finished a few months ago. Thank you.
Thank you very much. Questions?
We have to compute all the contributions for the height.
Yes. No, you don't do this way. You just show that the difference of them does not belong to the thing we care about it. Because at the end of the day, we need to take the Pearson product with 3 custom form we know. So we just show the difference has a product with this. That's again we use the local representation figure. because the dichotomy said epsilon facts. So inside we call it coherent, not coherent. Coherent means that the form contributes special value form. Incoherent means the form contributes the derivatives. So the two space is one for the coherent, incoherent. So one is for sign 1. It's a function of sign 1. Other one is sign -1. We show the difference. Okay, when I say equal, it's not quite correct, not equal. The modular coherent forms. Coherent form is this form contribute with sign function equation is a 1.
My question was more about computation of these balance, block balance on height.
Yes.
Do you have to compute all the contribution at all times included infinity, or?
Yes. Infinity and the good prime you compute first. That's very fast. Actually, for good prime, you're already done by Gross and Keaton, I believe. He's done this thing already. Kingdom Place is a bigger mass, but it's also been done. Better one is hard. Oh, another question. My original talk is about the positivity of heights. This is another big question left over 40 years conjecture. And only until very recently, we have managed to show that if the cycle, algebraic cycle, move in the family, then almost all of them are positive. Because whenever I talk this kind of thing, Peter Sarnak always challenging me. Well, you prove a beautiful formula. Can you say anything for each size? Now we can say something. It's almost positive.
Questions?
So I have a very naive question. So you mentioned that when E1, E2, E3, they are equals, then the derivative is 0, right?
Yes.
And how about higher derivative?
E1, E2, E3. Let me say what I'm trying to say. Because you can this tetromodule, it becomes they're equal. You can have a precise decomposition. Your weight is 3 vanish. I don't know. High derivative, I don't know. Derivative vanish. The answer is I don't know.
I think we have time for one more quick question. No? Let's thank the speaker again.